Here I'd like to show you how we can carry matrix operations into application when we're dealing with geometric transformations. So first of all, I want to illustrate that through one type of a transformation that is called a translation. So recall that a translation is just a slide of a figure, meaning that you're going to move the figure just some combination of up, down, left, and right. So you're not actually going to like contort the figure, you're not going to stretch or shrink the figure at all. It's going to remain exactly the same size, it's just you're moving the shape and that's all that you're doing. So if I were to say to translate this figure, and let's say that we wanted to translate it up 1 unit and left 3. Then basically if I just kind of go up 1 and left 3, so I moved that dot to there, and then I go up 1 and left 3, and then up 1, left 3, and up 1, left 3, those would give me the new corners. And then if I just kind of connect the corners right there, this would be the same exact figure that we had drawn, but now it's just moved up 1 and left 3. So it turns out that we can kind of model this using matrices. So if you organized in a matrix the data you have, so really just kind of the vertices of the matrix, so like I have the vertex 3, 4, and then I have the vertex 1, -2, and -2, -3, and -1 and 2. And then if we're going to translate this up 1 unit, really that means the y's are going to increase by 1. And so since these numbers right here are the y's, I really just kind of want to add 1 to all of them. So here in the second column, I'm just going to put 1's right there to add. And then because we're going to go left 3, that really means we're going to take away 3 from the x's, so subtract 3. So I really want to add -3 to all of this. And then if you actually carry out that operation and you perform that operation, you're going to get 0, 5, and then -2, -1, -5, -2, and -4, 3. And it turns out that that matrix right there are actually the coordinates of the vertices of the new matrix, because you can see like 0, 5 actually ends up being that dot right there, -2, -1 is that dot right there, and -5, -2 is right there, and then finally -4, -3 is right there. So kind of a neat way that we can use matrices in the context of translations. And then I want to show just kind of one more geometric context in which we can use matrices. And I want to illustrate that here through what we refer to as a dilation. So a dilation does actually like stretch or shrink the figure, but all aspects of the figure gets stretched or shrunk accordingly. So if we were to, let's say, dilate this by a scale factor of 1/2, then that means it's actually going to get smaller because you're just going to kind of half everything. So the way this would actually work with matrices is you would take some sort of organization of your coordinates. I'm going to just have the same matrix I used earlier to record the current vertices of our matrix. And then all we would do to dilate this by a scale factor of 1/2 is just take 1/2 and times it with the matrix. And so we're going to end up getting then like 1.52, and then 0.5, -1, -1, -1.5, and then -0.5 and 1. So if I plot these kind of pairs of coordinates now, so 1.52, that's going to give me this point right here. And then if I plot now 0.5, -1, that's going to give me, there we go now, yeah, 0.5, -1, there we go. Okay, that's the purple dot. And then if we plot -1, -1.5, then that's going to be this dot right there. And then finally, -0.51 would be right there. So really you can kind of see how like that dot moved in that way, that dot moved in that way, that dot moved in that way, and that dot moved in that way when we apply this scale factor of 1/2. So now if I just connect these 4 vertices together, it gives me just kind of a similar shape, but now just like everything's kind of been dilated by that scale factor of 1/2.